Welcome to Rust Belt Science. I'm your host, Maggie Fink.
And I'm Shahir Risk.
Today we have with us a very special guest. We have Bahram Moasser, who is an associate teaching professor in the Department of Chemistry and Biochemistry here at the University of Notre Dame. We're very excited to have you. Welcome.
Well, thank you for having me.
Yeah, of course. So the first thing we always ask our guests is, are you reading, watching, or listening to anything right now? It doesn't have to be chemistry related. Could be something for fun, anything interesting that you just kind of want to start off with.
Sure. Well, during the semester, it's hard to really find time, but I sort of put things aside for things like fall break, spring break, and the summer. And over the fall break, I caught up on two poets that I had my eye on, that I had read before, but I was really eager to sort of follow up on. And one is Jules Supervielle, who is an Uruguayan French poet. He was born in Uruguay, raised in France, returned to Uruguay. He writes in French. So I read the English translations. My French is not strong. I can read French, but it's not so strong. So I read the translations. And the other is Louis MacNeice, who is an Irish poet and playwright. And I bought their books, Anthology of Poetries, and they were sitting on my shelf waiting for the right time. So fall break, I immersed myself in these two. It was really exactly what I needed. And what I was hoping it was going to be. It was really very, very gratifying.
Are they modern poets or?
They're 20th century poets.
Okay.
Supervielle is interesting. He is sort of in the time of the surrealists,
Okay.
but he is not one.
Okay.
He sort of bucked the trend, and he writes it's very imaginative. And I'm not sure if this is correct. I would call him a symbolist. He writes sort of by conjuring images. A lot of times within the same poem, ideas mix. Without you knowing it, you've gone from one idea to another. And in some poems, he actually writes short prose. It's almost like a prose poem, somewhere between a short story and a poem, where you start off thinking that this is in the real world, and then you find yourself in a fantasy world and a world of unusual imagination, and just really kind of interesting, very imaginative.
Okay, I'm going to add those to my list. I love poetry. I haven't gotten to read as much as I would have liked to lately, but I used to read it all the time, especially when I was an undergrad. So I am excited to add some more to my list, and I'm always trying to find kind of not as famous ones to explore as well. So
Sure.
Yeah, they're on my list now.
Yeah, it sounds lovely.
Yeah. Do you have a favorite poet that of all time, or is that too
Too narrow
of a question?
It's hard to say because I read poetry of different cultures. I read Iranian poetry. I'm a native Iranian, so I read a lot of Iranian poetry. And my favorite is, I have two sort of favorite styles. One is classical Iranian sort of Sufi poetry. Rumi, for example, is the famous one. I love Rumi very much. And the second is what was called modern Iranian poetry, poetry in the 1950s, 60s, and 70s. And during that time in Iran, in poetry, in film, in art, there was a sort of a cultural revolution or artistic revolution where, alongside other movements in Europe and South America, in America, other places, Iran was developing its own unique type of modern art, especially modern poetry. It was called New Poetry. And I think if that had continued, if it hadn't been interrupted by the revolution and everything else, history books would have written it as a distinct kind of modern poetry. It was very special. It was sort of had things in common with movements that were going elsewhere, but it was distinct Iranian new poetry. So both new and old in that sense. But as far as poets, I mean, I love Walt Whitman.
Yes. Yeah.
And William Wordsworth, Byron, all those poets. But like you, I'm always searching. I was looking for new poetry.
Very nice.
This makes me so happy. We were Shahir and I are both like, oh, we want to talk about poetry, and that's the first thing you started with. So you delivered, and you're not even here to talk about poetry. You're here to talk about chemistry and art in all its forms. But it's so cool to have somebody who is a scientist, a chemist nonetheless, come in and be able to talk about something like poetry so proficiently. I think it's not something that we find in a lot of scientists, or they're not as open about exploring those other things as well. So I'm so excited.
They might not be as open, but scientists, I think, have always been interested in art. And when you look at the great scientists, Einstein, others, they've always had artistic streaks, whether they actually performed art or were lovers of art.
Right.
It's always, I think, been artists have always been interested in science, and scientists have always been interested in art. I think it has always been a two-way street.
And a lot of people might not think that, but that seems to be the reality. And a lot of the Nobel Prize winners in sciences have some really serious artistic talents and pursuits. That's just been what's been evident.
Yeah, absolutely. And two of the most famous scientists of the 20th century, Ed Wilson, who's a biochemist, entomologist, ecologist, everything, famously admired ants. He talked about the unity of knowledge. And he is an unusual person. He won 2 Pulitzer Prizes as a scientist, writing, about science and communicating science to people. And he talked about the unity of knowledge. And the same phrase, the unity of knowledge, was used by Glenn Seaborg, who is one of the most famous chemists of the 20th century. He sort of was a father of transuranium elements. He did a lot of work in nuclear reactions, in understanding the nucleus as an element named after him, Seaborgium. And he also talked about the unity of knowledge. So they, from their mouth, they are authorities in science, and they're talking about how everything comes together.
So you are a chemistry professor, and you teach lab courses and you teach lecture courses. And chemistry can be scary to a lot of people, especially people who are outside of the sciences. And a lot of students, I teach chemistry as well, so does Maggie. And a lot of students who come into chemistry, they might not be pursuing chemistry as their major or as their career, but inevitably they have to take chemistry. And it can be really scary and, kind of a little bit, they can be a little bit apprehensive about it. But what attracted you to chemistry? Were you always interested in going into chemistry, or was there other things? And how did you end up being a chemist?
Well, I think my story is not unusual. I fell in love with chemistry in high school because of my chemistry teacher. I had a absolutely incredible chemistry teacher by the name of Carol Stearns, Dr. Stearns. I had her for 2 courses, chemistry and AP chemistry, and she was just a unusually gifted teacher. She was a incredibly kind person, and I think in high school I didn't fall in love with chemistry. I fell in love with chemistry in college. I think in high school I fell in love with what a scientist is. The behavior of a scientist. How a scientist thinks and pursues knowledge through observing my teacher. And I think I fell in love with being a scientist at that moment. I owe it all to her. I decided at that point in high school that I wanted to become a chemist. And I've never looked back. I've always sort of had a passion for science, but it's hard to put into words. Speaking of Walt Whitman, he famously said, "One word can pour a flood into the soul."
Mm.
And I think Dr. Stearns had a way of flooding your soul with the words she chose, with the way she described things, and the love she had for science. So I think I fell in love with being a scientist in high school, and then I fell in love with chemistry in college. And everything I did was exciting to me. Every course I took, every interaction I had, I joined the lab, started doing research. It all seemed just impossibly good. It just seemed wonderful. I mean, it was just this world that opened. And, I took general chemistry, loved it, took organic chemistry. It was like, wow, this also exists. It's like biochemistry, everything. It was just a wonderful experience. So I really got immersed into it and really got pulled into it. I don't remember a time I didn't want to be a chemist.
Yeah. And so you point out the importance of a good teacher to really spark that interest in science in general, but also specifically in chemistry, because it can notoriously be scary or turn people away from it. And I think that that's generally true. I think for all of us. Speaking from my personal experience, I actually hated chemistry in high school, and then when I went to college, I fell in love with it because of the teachers that I had. And I think that so how can a teacher make such a big difference? And I'm not necessarily asking what did this teacher do differently, because you described it very well, but what is that effect, or where does that come from? And if you are a chemistry teacher out there and you're listening, or if you're a chemistry student out there, how much of it is from the teacher point of view, how much of it is from the student, and what can we do as chemistry teachers? What do you do?
I think, there are a lot of students who are apprehensive about science in general, chemistry in particular, and with students who are taking chemistry because they have to. For example, for 7 years I taught the non-majors course. This is the second general chemistry for second semester sophomores at Notre Dame. And in that course, if you're in that course and you're non-major, you're a pre-med. You're basically everyone else has left the non-majors track, chemical engineers, everyone else who takes non-majors chemistry. So at that point, you're a pre-med. And you're basically taking this course mostly because you have to satisfy the requirements. Some may actually enjoy it. But, I tell my students, I don't teach that course anymore. I taught it for 7 years, but I used to tell my students on the first day of class that they're here. They may not have a love of chemistry, but they have a love of learning. Yeah. And that's our common bond. That's where we meet. And if they're willing to give it a chance, that they'll find that there's enough here that is interesting, that could spark their curiosity, and it's hard work. There's no way around it. Chemistry is a difficult topic, right? But if you have a love of learning, I think you can push through, and you can sort of find the things that you find interesting. I think when you learn with joy, you learn more deeply, right? And what you learn becomes more enduring. It becomes more permanent. So I think that's what happened to me. I learned with joy. Yeah. And I think if that's what I can do in a classroom, or any teacher can do in a classroom, I think that's probably the key. I think, again, based on my own experience, I fall in love with ideas. Yeah. And I think that's how I try to teach. If students fall in love with ideas first, then they're willing to do the hard work.
Right. So do you think that sometimes the students are kind of stuck in the details of it, not seeing the big picture or not seeing the big idea, as you put it, that they're more concerned with memorizing how many bonds does oxygen make and how many electrons does it have, rather than missing the point of what oxygen does for us as living things, and how it came about, and so how much of that are things that as a teacher we should talk about?
That's a great point. I think there should be a mix of things. Drawing from a research experience, for example. In research, there is the daily things, the day-to-day experiments. Some of them are repetitive. Some of them are, you run into troubles. There's, instruments break. There's all sorts of things that you have to do. Then there's the practical things, kind of the intermediate things, setting up an experiment, design of experiments, and so forth. Then there's the higher level things, the ideas.
Yeah.
You have to do all of them.
Right.
And you have to be able to go in between all of them.
Right.
I think the same approach should apply to teaching.
Right.
There are daily things, there are intermediate things, and then there are grand ideas. Yeah. And you have to have all of these. And I think the hard work, getting through sort of the problem solving, getting through the mechanics of chemistry is very important. And if you do that, it allows you to understand. It opens up doors.
Right.
For example, this semester I'm teaching 2 labs. I'm teaching a freshman lab and a senior lab. And to my freshmen, I told them, the first day of class, I told them that science beyond everything else is about imagination and creativity.
Right.
And these past couple of weeks, we've been producing a lot of data. Yeah. Titration curves, Beer's laws, job plots. These things take a lot of work, a lot of careful measurements, a lot of dedicated attention. I'm walking the labs and it's quiet. Everyone's like sort of really in the
in meditation,
zone. Yeah. Being very careful about their measurements, and data looks wonderful. I mean, unbelievable. Wonderful. It's like textbook stuff here.
Beautiful.
And I told them that I stand by my word. Chemistry is about creativity and imagination, but it starts with data.
Yeah.
It allows you to use your creativity and imagination. So you have to have the mechanics. You have to have the basics.
Yes.
And it opens up doors. So I think, again, drawing from a research experience, being in different levels at different places is always a good idea.
I really like this idea of being able to move from different levels, looking at the minute details, and then being able to zoom out and see the big picture, and then come back and focus on a small detail or the mundane things, or identifying where the failure is, and then go back and look at the big picture and say, are we missing the point? At some point, I think in one of my courses, I said it's like when you're painting a mural and you're really painting the whiskers on the tiger, because what else would you paint on a mural other than a tiger?
A tiger, sure.
Right. But then you have to really be able to zoom out and see the claws and and that idea of going back and forth, not missing the point, but being able to handle that or have a handle on the details. I think it's really nice, and it's something, like you mentioned, something that we should really drill into our students early on.
Yeah. I going off of that and hearing you kind of talk about your love of chemistry and your love of teaching, I actually pulled a couple quotes from your LinkedIn about me that I really loved. And I want you to maybe expand on them, especially when it comes to chemistry, because we haven't had a chemist on here before. And I think chemistry, Shahir and I can talk about proteins and biochemistry, and there's a little bit more of a visual aspect to that. But chemistry, it's not quite as obvious, I think, to people. So anyway, you talked about how you're enchanted, about how rules and principles can be used to see the unseeable, which I thought was really interesting, because I didn't really ever think of chemistry as something you could see unless you got lucky and had a colored solution. And you also say that your taste in reactions has shifted. Chemical reactions, I'm assuming here, different types of reactions you can study, but the joy has never lost its luster. And that was the most poetic LinkedIn about me I've ever seen personally, especially when talking about chemistry. So can you explain, especially how the rules and principles can be used to see the unseeable and what that means to you? And maybe, for a lot of our listeners who maybe haven't thought about chemistry since high school, kind of bring them back to learning about those basics and why you fell in love with those.
Sure. I think that is really sort of where my love of chemistry came from. The idea that you can go into the lab and perform experiments in the macroscopic world on the benchtop to gain insights into the private lives of molecules, how they behave, how they interact with each other, the unseeable. One of the greatest examples of that is something called transition state theory. So the activated rate theory in general, the idea of how molecules transform from reactants into products. They go through this activated state, high energy state, called a transition state. And a transition state, it was proposed by Henry Eyring, Michael Pogliani, and Meredith Gwen Evans. And they proposed it as a mathematical construct. It's not something that exists. It's a picture of what may exist at the highest energy point in between reactants and products. But a lot has been made of it. Of course, in biochemistry, in enzyme catalysis, for example, a lot has been made of it. Very fruitful. I mean, it has been an incredibly rich, idea based on a picture that really you cannot see.
Right.
But there are quantitative ways that you can go into lab and make measurements to guess at what it may look like. You can not only guess at what this transition state may look like, you can even guess at how advanced bond breaking or making is, what relationships are, what bond angles are, what atoms are close to each other or not. None of that is seeable. But you can go into the lab and perform experiments to gain insight and see the unseeable. And I think that's the best example of what I meant by that. And this idea of connecting the macroscopic world of the laboratory to the microscopic world, the unseen world. You have direct insight into the unseen world by doing things on the benchtop, which is amazing.
Yeah, this past week in my organic lab, we did polarimetry with some chiral molecules, and it was really fun to see the students kind of like put two things, like you can see how the light is changing and measure it and correspond that to what an enantiomer would have. And it was really cool to something, I think NMR and IR can be a little bit vague. Those are other things we've been working on lately. But seeing the light and the polarimetry and they were pretty old machines. It was really exciting to kind of see, you can see it happening, which is not something that I remember getting to do as much in chemistry. It kind of always felt a little bit like, I don't get what we're doing. We're just mixing two things. So I remember when I first learned about polarimetry too, I thought that was really cool and it makes sense. And I also fell in love with chemistry in high school, and then once I got into organic chemistry, struggled a little bit to, not that I didn't have a fantastic teacher, Shahir and I actually had the same professor. Right. But yeah, it can be very difficult to visualize things that you can't see, especially if you're in a lecture environment, and then it doesn't always translate to the lab environment. It takes a while sometimes for it to click, I feel like. And this is a nice segue, I think, into this chemistry and art class that you teach, which is actually really what interested us in having you on here. We attended your talk that you gave a month ago, I think, at the library about this class and the intersection of chemistry and art and how you're using each one to teach about the other. So I'll let you just kind of expand and talk about that and maybe how you came up with it and why you decided to do this.
Sure. I think there are two things that I can talk about. One is the larger idea of chemistry and art, and then the reason why I designed this course. I think chemistry and science in general has great affinity with art, has always had. I think this idea that there are separate domains is a relatively new one.
Right.
I think they draw from the same well of creativity. I think scientists and artists are curious. They want to know about the world. They are researchers. Artists are researchers. Scientists are researchers, and um, they want to know about the world through creative endeavors. I think that is the link, and both embrace uncertainty in pursuit of originality. They're not afraid of it. They embrace it. And they use creative ways of uncovering the truth. I think fundamentally these are how a scientist and an artist, all the things they have in common. I think to be a good scientist and to be a good artist, you sort of have to start from a speculative idea. You have to start from a preconception. You have to believe in something that doesn't exist and, sort of pursue it. Right. And sometimes it doesn't exist. Yeah. So that's great. Yeah. Sometimes it does, and you pursue it. Yeah. You sort of have to, but you have to have this preconception, right? And a drive to do that. So, I think that there is an affinity between science and art generally. The reason to create the course, I think, was motivated partly by this, and partly by the fact that I feel like at Notre Dame, but I think it's the same everywhere in college, we are training students to be specialists. They are becoming very good at, tasks. They're becoming very good in their courses, in fulfilling requirements, and we're training people to be job seekers. Mm-hmm. And in my mind, I think college should be more than that. Mm-hmm. So my hope was that this kind of a course, this kind of an integration course, would be a model of interdisciplinary learning that would help students sort of synthesize a way of knowing that is more fundamental, that is not necessarily tied to a course or a task, but it seeks more fundamental things about learning. Mm-hmm. So my colleague and I, Michael Scheffler, who is a professor of art history and design, he's an art historian, mm-hmm. and I designed this course, and we taught it for the first time last spring, mm-hmm. and we're teaching it again this spring. That was the drive for creating such a course. I think there are so many things that are in common. And I think going back to the unity of knowledge, I think learning these fundamental aspects that are in common between art and science hopefully will help students live better lives, understand the world a little better, mm-hmm. and hopefully be a little bit more courageous. The title of the course is Only Connect, Chemistry and Art. And the Only Connect comes from E.M. Forster. Mm-hmm. It's the epigraph of a novel called Howard's End. Mm-hmm. And in the novel, Forster is trying to encourage this sort of a unity, this sort of a connection between the past and the present, between social divisions. That's a big part of the novel. These things that are in the exterior world amongst people. But really, at the heart of it is the belief that resolving these divisions in the exterior world will ultimately help resolve divisions in the interior world. Mm-hmm. And that was the idea of the title of this, Only Connect Chemistry and Art, that by learning these things that are in common between science and art, that students would learn things about themselves and about learning itself.
That's wonderful. I mean, I think we agree on this, that a big part of college is learning about who you are. And I feel like this is something that I experienced when I was in college. And I fell in love with that part and never wanted to leave college. And here I am, still in college, basically. So it's about learning a little bit more about who you are. So I love that idea. Can you tell us a couple of examples of things that are in the curriculum that connect chemistry and art? And how do you do it? And what's the reaction that the students have?
Sure. So the syllabus has 6 units. It's symmetry, light, shadow, negative space, perspective, um, color. We have a unit on restoration and conservation. And also, our last unit is called the origins of creativity.
Mhm.
So the idea is that having sort of examined these different topics, symmetry, perspective, and so forth, and see how they are related to art and science and chemistry in particular, how we can understand this unity of knowledge, that the two draw from the same source of creativity. So, for example, in symmetry, there are many examples in which artists use symmetry to add meaning to their work of art beyond that which is obvious. You can see that in artwork, in paintings, in poetry. In fact, in a couple of instances, we analyzed poems and saw how symmetry was incorporated in the poem itself that added extra meaning that perhaps sometimes was contradictory to what appeared to be the meaning of the poem. And in the same way, chemists use symmetry to great effect for resolving problems that appear very complicated. You can, a lot of times, by applying symmetry principles, solve very difficult problems more easily by looking at it in a different way. And I think that's the point. The point is looking at things in a different way by understanding the relationship of parts to the whole and parts to the parts of a thing, whatever that thing is, a work of art or a concept in chemistry. You can understand how you may be able to see, by preserving the symmetry of this object, but transforming it into a different space in which you can resolve the problem more easily. I think those are the things that are common in terms of symmetry.
Right.
Perspective, negative space, all of these things are ways in which chemists and artists use these concepts.
Yeah, and so one of the things that is a pretty famous example of things like symmetry is the handedness of molecules, and how some molecules are what we might call left-handed and some are right-handed. And this concept of what we call chirality, as you know, of course, is this ability of a molecule to exist in a left-handed or a right-handed form and be mirror images of each other. How does that mirrored, if you will, no pun intended here, in the arts, and how do you use that as an example to show the concept of chirality, which a lot of students might struggle with? It's easy for us to look at our right hand and say, yes, that's our right hand or left hand, but then when looking at molecules, that can be a little bit more difficult. How do you use art to demonstrate something like that?
Yeah, I mean, I think the idea of chirality is wonderful. And, as you know, a way of understanding chirality is by looking at mirror images. If something and its mirror image are not superimposable, they are chiral. Two molecules, for example, that are chiral, they have the exact same constitution, the same connectivity of bonds. They are in every way identical, except for their spatial arrangement of atoms in this very unique way that there are non-superimposable mirror images. And I think this has a lot to do with what it means to be a mirror image and what a mirror does.
Yeah.
I think artists have explored the idea. For example, if you look in a mirror, you see yourself not in the way that other people see you. You see yourself as the way you see you. For example, if you look standing in front of a mirror and you have a coffee mug in your left hand, your mirror image has a coffee mug apparently in the right hand.
Right.
But everyone else sees you as holding a coffee cup in your left hand. So what is happening is that there's a symmetry operation that's taking place, not in the real world,
Right.
in the mirror world.
In the mirror world. Yeah.
That there are two worlds that exist simultaneously, a real world and a mirror world. And I think this idea has been explored very effectively in science. Of course, the basis of most biochemical reactions rely on this idea of chirality. But also for artists, there are many examples of art that is chiral, whether it has spiral chirality or mirror image chirality of different kinds, to give a sense, to give a sort of again, a additional meaning that may not exist just by looking at the object. I think one of the ones that really sort of resonates with me, again, because I have such a love of poetry and music, especially Iranian poetry and music, is the Sufi dancers who whirl and they rotate, they put themselves into a trance. As poetry is being sung, there's a classical ensemble, sometimes in groups, sort of the whirling dervishes, and sometimes individually. And in Iranian Sufi tradition, you always whirl counterclockwise. You move to the left to go to the right, because the left in Sufism is considered to be the spiritual, and the right is considered to be the material. In a sense, what you're doing when you're whirling counterclockwise is you're seeking the spiritual world to understand the material world. And if you watch the whirling dervishes, it's always a counterclockwise whirl. And this is a choice. This is a philosophical choice, because you could easily have whirled clockwise. Right. And in a sense, that could be a completely different philosophy. It could be more of a Hegelian way of thinking, where you would seek the material world, what exists as real in the material world, as a way to find the spiritual
world.
So it's a choice to whirl counterclockwise or clockwise. That is chirality.
Wow.
So I think you make a really great case for using art to teach science, in this case specifically chemistry. Can you talk about the value of scientists? Because I know some of the scientists, or some of your students are science majors, some might be art majors. But what is the value of scientists learning about art outside of, understanding, for example, the symmetry or this chiral molecules? Because, in listening to your talk, I learned a lot about art that I didn't know, or, new ways to think about art. So how important is that flip side of what you're doing, do you think?
I think it's very important. I think learning about the shared values, the shared knowledge, the beliefs is important, but also learning about the creative process is important. I think scientists too often in the pursuit of science, they sort of become very focused, very tunnel visioned, and they stop sort of seeing the bigger picture. And I think art sort of opens up the bigger picture. It opens up the creative world and emphasizes, underscores the need for that. I think every scientist, got into it for the same reason, for the love of knowledge, the love of creativity. And I think to remind yourself of that all the time, I think is important. I think artists and scientists pursue the same thing.
Yeah.
They pursue, they are both ways of knowing.
Yes.
And they have a lot in common in the way they pursue knowledge.
So you mentioned how you're consuming a lot of art and you're reading poetry, but are you producing art? Do you write poetry? Do you paint, play music, all of the above? Anything else?
I write.
Uh-huh.
I write for myself. No one's ever read anything I've written. I write for myself sometimes, just short things. I write short poems. I do want to paint. I don't paint, but I do want to paint. That's on my list of things to get to.
Yeah.
I don't. I play the piano, but I haven't in a long time. But I listen to a lot of music. I think I'm more of a consumer of art than a producer of art. But I do love to write. I love words. I think to me, language is the supreme way of communicating.
Yeah.
You know, I think today image has supplanted word as a way of communicating knowledge. But to me, it is always about words. It's about language.
Yeah.
So I do write, and I think it makes me a better scientist. I think because writing, putting your thoughts on paper, is an act of thinking.
Yeah.
And you know, when I write my lectures, I put pen to paper.
Yeah.
I write out my lectures as an act of thinking.
Yeah.
I never lecture from notes. I have never lectured from notes. So they're not there when I'm teaching.
So you're not there to read them.
They're not there to be read.
Just to pour out the thoughts into words on a piece of paper.
Yeah, exactly.
Very nice. So is this something that you encourage scientists to do, to not only consume art, but maybe try their hand at producing some sort of art, even if it's not something that they want to share with the world? Do you feel like, and I'm hearing that you're saying that this helps you as a scientist. Is this something that you think all of us scientists should be doing?
Yeah, absolutely. In fact, some of the most famous scientists do this. Roger Penrose, a famous physicist, famously doodled. And you know, more than doodle, he sort of distilled his thoughts into these images. And you know, he has notebooks of images and a parallel set of notebooks of formulae. They are the same thing. One is in image, one is in math.
And math.
So yeah, absolutely. I mean, and an example I love is of William Butler Yeats, where he put his thoughts into images, and he doodled. He famously doodled this double gyre that sort of expressed his sort of idea of dualism, idea of things that start from a point, they expand, and as they expand to the maximum point, that's a point of origin of another thought that then expands outwards. So these double gyres are coming together. I think, you know, not only for clarifying your ideas, but just to the act of painting, the act of writing, I think is a act of creation, and it helps.
Do you think that science today has shifted from you know, you were talking about your students and everyone's becoming so specialized? Do you feel like scientists today have deviated from viewing science through this more creative lens and are kind of just produce the data, get the funding, produce the data? Or do you think that, you know, do you see that happening, or do you think it's still there and I'm just not meeting those people who are, you know,
or we're just not talking about it.
Yeah,
like everybody's doing
know,
it. They're just kind of like.
I am currently, you know, a postdoctoral researcher, so I am in the thick of doing the research, and it can be really difficult to find the time to be creative, consume creative things, because that does feed into research, and you know, it can just feel like a grind a lot of the times because it is so much more competitive, and the pressure to come up with an idea takes away the time needed to think of a creative idea, I think, and think outside the box. I don't know. What are your thoughts on the current state of science and creativity? That's a big question.
Well, you know, I teach undergraduates, and I think that they have a large appetite for it. I think for students, the idea that science and art are related to each other is intuitive. They don't need convincing. I think what happens is when you go into sort of the apprenticeship stage of your life, whether it's law school, medical school, graduate school, you unfortunately you make a trade-off of depth for breadth. You give up breadth for depth, and you become very focused because you have to.
Yeah.
And then a postdoc and so forth, like you said, it becomes very competitive. You have to produce all the time. So I think the instincts are there. I think the instincts sort of get pushed back because of the reality of the situation of funding, of jobs, and so forth. But one thing I do is, what I've known about myself since childhood is that I require idle time. And in order to produce idle time, in order to sort of carve out that time, I have become incredibly efficient at what I do. So when I'm at work, I'm very efficient at the things I do. I get work done. I was the same way in graduate school because then I can carve out some time and do nothing or do whatever I want to do, listen to music or write, do nothing, just think. And that, to me, pays dividends many times over. I know that you talk about the time it takes. If I spent that time that I was doing nothing, doing research, doing work, it wouldn't have been as productive. But taking that time to refresh my mind, to re-energize, makes all the other times 10 times more productive.
Right.
It's very difficult to convince someone who's in graduate school to take a risk to do that.
Yes, that's true.
But if they take the chance, I think they will find that doing that would pay dividends in the long run.
Right. So basically, having that creative time was a motivator to be more efficient and more effective, but then actually taking that time makes you more effective and more efficient.
Yeah,
and
absolutely.
Yeah. When I was in graduate school, I was in a blues band because they were looking for a bass player. And I think it really made a huge difference in my outlook because, you're working in the lab the whole time. It's very hard to get out of your head. And just having the time to do something creative, especially with another group of graduate students and kind of sharing the the struggles, if you will, of, oh no, my experiment didn't work. Oh, really? You too? Oh, yeah. But then doing that collectively in a creative group really helped all of us, and it was very evident. So yeah, it's something I definitely agree with you on.
Yeah, absolutely. And I think another thing that I practice is as much as I can, I go with how I feel. In other words, there are some days where I just feel like doing mechanical work, and that satisfies me. I just want to do things that are routine, set up the lab, do the things, make the reagents, stuff like that. Just the way I feel.
Yeah.
Other times I come in and I feel just incredibly creative, and I go with it. And I take that time to think about lectures, to think about future experiments, future lectures, designing courses, thinking about things. I go with how I feel. I don't try to disrupt it. I don't try to go opposite the way I feel. Of course, you can't always do that.
No.
Class starts, reagents have to be there.
You gotta be on. Yes.
Students are going to be there.
Right.
So, but as much as I can, I go with how I feel.
Yeah, it's a type of honesty with who you are, honesty with yourself. Yeah.
Yeah, I think it's kind of the opposite of how we think about scientists. Sometimes it's very robotic. People that don't feel, and we just show up and do the same thing, and sometimes I don't want to do anything at all, and that's needed time to do nothing at all. It's hard to convince people who pay you money that you need to do that, but it is really refreshing to hear somebody say that. It's like, yeah, if I feel creative, I'm going to do the creative things, and sometimes I feel like just setting up a bunch of experiments in a very robotic way because that's very rewarding.
Right.
I don't know. I really like that you said that, and that's really encouraging that people should do that. We're humans, and we're not going to wake up feeling the same way every day or have the same. How many ideas have I lost because I didn't take the time to just sit and write them down and be creative in that moment?
Yeah.
So,
and just allowing them to grow in your mind and just giving them the time to grow as you would a plant or, a pet or something.
Yeah, absolutely. Absolutely.
Yeah. When we talk to other people that we've had on the podcast who do research, we kind of ask them, what's like one concept or one idea that you'd like our listeners to take away from this conversation? We had Lee Haynes on talking about insects and what people can do to make the world better for insects. And with Dr. Deb Moore, talked about leaving the leaves and planting native plants. Since she's an ecologist. So with chemistry, it's maybe not as practical of a thing that people could take away from this, but is there something about chemistry that you just wish people could understand, or something really cool that they could take away from this conversation?
I think I can answer that on different levels. As far as chemistry in general, I hope people would understand that chemistry is everywhere. And it is multifaceted. It's unique in the sciences in the sense that it's sometimes called the central science, and that's a misunderstood statement. Many people think that means it's the most important science, and that's not the sense of it. The idea of the central science means it's more connected centrally to other things. And I think it's because of the scale. Chemistry occurs on the scale of atoms and molecules.
Right.
It's in between physics and biochemistry or biology. And on the scale of atoms and molecules, there are things that happen that there are ideas that are just incredible. There are ideas that, if you really try to understand them, even as a layperson, someone who's not a scientist, if you grab a book and try to understand, they're wonderful. They're wonderful not only as a chemistry idea, they're wonderful as a life idea. Of course, there are very deep things in physics. Physicists can talk about, very deep things. Of course, biologists, same thing. But I think in the intermediate scale of chemistry, there are these beautiful ideas that you can take away from them. And one thing that I wish that more people knew about, I think it's important on many levels, is the idea of entropy. If I ever wrote a book, a chemistry text, either for college level text or a general audience, the first section of the first chapter of the book would be on the second law of thermodynamics. I think it all begins and ends with the second law. I think the idea of the probabilistic view of the world, the idea of not having discrete understanding, but being able to have a statistical understanding is so important. And I think the 20th century, whatever feeling was there in the beginning of the 20th century encompasses all of that. Movements in art like Cubism and Dadaism and, experiments with probability and chance and all these kinds of things really sort of shattered the idea of sort of the Newtonian world of we have equations for everything.
Right.
To change that to we have probability distributions for things. And I think that concept, if conveyed properly, to a general audience, can be very powerful in understanding the world. Right. I think that is something I wish more people would know about. One of the activities we did last spring in the OmniConnect course. I think it was one of our last activities was students were to create a work of art in which the element of chance was playing a huge role.
That's cool.
And
that's super cool.
They had to design it. Again, it wasn't like chance was just a peripheral thing. Chance had to be a central idea. And students did so many creative things, just unbelievably creative things. One student, Rocio, she took a painting that she had made. She cut up in pieces, threw them all in the air. They fell down, and she glued them where they had fallen down. She allowed chance to create the painting.
Wow.
And then she did some tracing and so forth. Another student, Julia, what she did is absolutely gorgeous. She set up her sketchbook with a whole bunch of colored pencils on strings and took it outside on a windy day. And all these pencils were moving in the wind, and they were creating an image on the paper.
That's super cool.
It's absolutely wonderful.
Yeah.
And she allowed chance. She allowed the wind to create the painting. And I think the idea of probability, the idea of chance, and how important it is, and how fundamental it is to chemistry, to science in general, I think is something I wished more people would be aware of.
Well, I definitely, if I were to hope for something, I wish that you would, I really hope that you would write a book about this, especially something for a general audience, because I think there's often a disconnect between these fundamental ideas in chemistry and physics and biology that are so fundamental to all of us in the fields. And it's almost like we hold them close to ourselves. We see them in a certain way. But, the good news kind of never gets out in a sense.
Yeah.
And I think, having very creative people like yourself, I would definitely read a book about this if you were
thank
to
you for
write
saying
it.
that.
Absolutely.
Yeah, I think, again, hearing you speak about this when we went to your lecture at the local library, I've never heard anyone talk about chemistry the way you talk about chemistry. And I've had some excellent chemistry professors.
Yeah.
So that's no knock against any of them. But the way you speak about it is so lyrical. It's so hard to describe, and I'm blown away. I was actually very nervous about this interview because I'm just so in awe of how you're able to do that. And I think, especially in the field of chemistry, it's very difficult to do. It's much easier to talk about biology, I think, because there's so much visual and inherent to even down to microbiology, right? You can still see those things. Chemistry is so much more elusive, and the way you describe it makes me remember why I first liked it when I was in high school, and it's really inspired me to how I interact with my students as well with chemistry, and just continue to be like, guys, this is actually really cool. If we stop, like, let's not focus on what's my grade going to be, how can I get more points, or just stop for a second and let's experience the joy of this process. And I am very much inspired by you. And
thank you for saying that.
I would also love to read a book you wrote. I think it would be excellent, and I would give it to everybody I knew, because chemistry is so cool, and it is. We couldn't do biochemistry, and I couldn't do microbiology without it, and we just kind of take it for granted sometimes, and are just, pass the class on to the next thing. So I really appreciate you doing this, and really, I don't know anybody else doing the types of things you're doing with science and art, especially chemistry. So,
well, thank you for saying that. I appreciate it, and I think for me it comes back to Whitman. One word can pour a flood through the soul.
Right.
I learned chemistry through words, through language, and I think I owe it all to that. If I look back on the chemistry texts that I had in high school, for example, they barely had any images, and the images were kind of hand drawn, or almost hand drawn.
Yeah.
Everything was described in words, and it wasn't necessarily that the words describe something discreetly or specifically. It was how they described them. And I think that's how, I began to fall in love with ideas.
Yeah.
And I think that's what I owe it to.
Right. And just adding to that, or going off this idea of words describing things, and going after what Maggie was saying about something like biology, it's very easy for us to talk or think about trees, things that we've known before we even had words for trees, since we were children.
Yeah.
But something that is like seeing the invisible, as you put it, something that is so fundamental but yet so elusive, we really need those words, and we need them to be as lyrical as possible, in some cases even poetic, to really get that feeling, to be able to be in the right space, to be able to understand those concepts.
Sure.
Yeah.
And I think it goes back to the love of learning.
Yeah.
I mean, even a non-scientist, even someone like a non-major taking a course in chemistry because they have to.
Yeah.
Most of my students in the non-majors courses, they don't love chemistry.
No.
But they do love learning.
Yes. And usually on the first day of class, when I'm teaching those non-major courses, I ask everybody, why are you taking this course? And they always say, because I need it for my degree. And I say, well, let's work on that a little bit, and say, maybe phrase it a little bit. And then it becomes this exercise of, lowering that anxiety level that people come into with trying to learn something like chemistry, and try and increase that excitement about learning, that love of learning as well, which, it's not always very easy.
Sure.
Yeah. Yeah.
I mean, students are under so many different pressures,
right?
And I think that what they learn from senior students, and then those who have gone to graduate school, and those who have gone to medical school, etc. The word comes back that do things that can be measured, because people count things,
right?
And so no wonder they're learning this, So a course like Only Connect, I think the point is to sort of push back against that idea.
Yeah.
Nothing here is being counted. This is a university elective with no prerequisites. Anyone can take it.
Yeah.
And, it's not a matter of grades. It's not a matter of, it's not going to be a big deal on your transcript. It's just for you.
So I guess, how do we incentivize universities and students and educators to really incorporate that model a little bit more in other places, and really kind of generalize it, and really have people see the value of it? Because like you said, things have to be quantified and counted. Everything has to be a line on your resume, or a check on a box. How do we actually incentivize, if that's even the direction you want to go, to kind of expand on this, or use it as a model for other places to build on?
Well, it's certainly difficult to do. I think I see signs, hopeful signs. I think a lot of universities, colleges are going back to sort of the liberal arts model. And I think because it works, because it produces complete human beings. And I think, as far as science is concerned, the humanities are at the heart of the liberal arts.
Right.
But to incorporate science into it, students have to be convinced that there's something humane about science.
Right.
That it teaches you more about the facts and principles of chemistry, that you learn about learning, and you learn, more importantly, about how to learn. And I think incorporating that into teaching science, teaching chemistry in particular, I think is very important. And when students learn in that way, with joy, with gratification, they are emotionally as well as intellectually fulfilled. They become more exuberant human beings. They become more fulfilled human beings.
Right.
And I think that's the kind of person we want in medical schools, in graduate schools.
That is the kind of person I want to be my doctor.
Yeah. Exactly.
For sure. Yeah.
Exactly.
Yeah. And in fact, there are some measurable outcomes, as I'm sure you're aware of let's talk about doctors, for example. Doctors who get training in art appreciation or art history statistically do better in looking at things like X-rays or or MRIs
Sure.
and be able to point out problems far better than those who don't get that art education. So there are actually measurable outcomes.
Yeah,
I
absolutely.
just don't feel like they're really advertised as they should be.
Yeah, I think the same is true for graduate school. I mean, in graduate school, one of the things I learned was how to create ideas.
Yeah.
How to create a hypothesis, for example, how to create new ideas. And I don't think anyone can teach you that. I think you learn it by being in the middle of it. A lot of it is sort of nonverbal communication. You see people talking, you see interactions, you see it in action. Sort of, there's so much that you know that you don't know how you know.
Right.
You don't. It was never written in a notebook. It was never in a textbook. It was never in a lecture. You picked it up.
Yeah.
And it sort of, in a sense, it reminds me of kind of a Gestalt theory that the brain completes the picture.
Yeah.
There's a closure. You get a little bit of this, a little bit of that, but in the middle, whereas there's nothing, the brain completes the picture.
Fills in the blanks.
Fills in the blanks.
That's beautiful. Yeah.
And I think the more creative you are, the more prepared you are for that kind of learning, the better you will be in graduate school.
I think that's true. I in undergrad, right before I went to grad school, I was reading a lot of poetry. That's when I first started doing some painting, and grad school was hard, but when I got there and the world did kind of open up. It's like, all right, here's your time to really explore, be creative, come up with new ideas. I felt that creative energy from being able to consume and make carried me through a lot of grad school. It was still very difficult, and I wanted to quit a lot, and I didn't have the time to devote, or even if I did have the time, didn't have the mental energy to really produce or consume anything. But other students who are struggling, I'm like, go do something creative, like get out of the lab, just go to the Racklin Murphy Museum here, go explore, go listen to music, because being a successful scientist really does demand so much creativity and ability to come up with a new idea, which, as you said when we started, is the same thing that an artist does, right? Making something that's new, a new idea. And I think we undervalue the time it takes to do that well. And it doesn't just happen by putting your nose to the grind. There's a time for that, obviously, especially in graduate school. But I felt much better off and enjoyed my research more because I felt like I had developed a creative habit that now I need to refine again now that I am done. But that's why we like having people like you on here to remind not just scientists, but everybody, who, no matter where they are, should be engaging in these creative practices that do make us feel more complete and whole as humans.
Yeah. You said something really important. You said you wanted to quit a lot. And I think everyone goes through that. And it's good. Self-examination is a good thing. To question your motives, to see if you're still on the right track, you still want to do this. Again, I think the more prepared you are, the better you will be to question yourself.
Right.
Yeah.
Because you will be able to question yourself without being critical of yourself, which is a skill that you learn when you think creatively, without beating yourself up, without being critical of yourself. You question whether your motives, your intentions, and you can really do that openly and honestly. I think if you are educated in this sort of a liberal arts way.
Yeah. And I think this is a theme that kind of comes up a lot on this podcast, is that science is just a whole lot of failure that eventually you kind of get used to, maybe.
Yeah, I would say so.
But then that's the whole point, is that you're trying to, it's just you're at the very, very edge of discovery. It can be a very lonely place, and you don't have, like you said, no one really teaches you how to create ideas. You have to allow your brain to fill these in, to fill these gaps, and then you go and try these things out in the lab or on a computer or whatever it is. And sometimes those don't work either. And so you just have to keep trying. It forces you to kind of be more and more creative, and it throws you in the deep end in a sense and says swim back. So that is kind of a recurring theme on this show about failure and overcoming that. And you're absolutely right that having that creativity really helps you out a lot. And I remember starting graduate school as by far not the smartest person, but I felt a lot more prepared because part of it was my undergraduate education and the teachers, professors who were very dedicated and really made a point to make me more prepared for the next step, as opposed to just saying, here's the thing, now go. But also a big part of it was the people that I hung out with when I was in undergraduate. It was a very diverse group of people who were business majors, they were art majors, they were literature majors, a lot of music majors actually. And we just talked about everything. We talked about philosophy, we talked about how we approach our own studies, what we read and what we consume, and and what we dance to, and it just like you said, it makes you more of a human rather than just a specialist.
Yeah, absolutely. So the more contact you have with different people, the better it is.
Absolutely.
I did the same experience in college. I lived in a house, not a frat, just a big house. This person, landlady, just rented rooms to a bunch of people. So there were undergrads, graduate students, just everyone. And, there's so many different experiences that you share with people. One of my friends was in hotel school, and, just hearing him, discuss his courses and the way he interacted, it was very different than, the way I did things, but I learned a lot from him. There was another guy, he was a math graduate student. And one day, I was in his room, we were talking, and I saw a bunch of notebooks. And I said, yeah, what are these? These are, you're writing your thoughts on, coming up with new math, theorems and so forth. He said, no. He had written, there's a bunch of notebooks, right? He had created a new form of government.
Oh, wow.
Oh, wow.
In his spare time. That was his hobby. He had redesigned a way of government. It's like, you're kidding me.
Wow.
So it's so cool to interact with different types of people.
Do you have this guy's phone number?
Yeah.
I lost touch with him, but I wish. I don't know. I don't know where he is.
Yeah, my grad school experience was a little different because I had kids and went back to school later in life. But just this idea of shifting your perspective on something like even interpreting data. I did a lot of microscopy, and so I would take my images to probably was at the time maybe 8 or 9, and be like, hey, can you describe the differences to me? Or what do you see? What is, I know what the conditions were. I knew what I was seeing. I was like, what do you see here? And I would take what he said and I would actually add it to my presentations and say, this is what my, child who has no idea what he's looking at sees. This is what he describes. And it really helped me approach, especially something as visual as microscopy, a little differently. And then really get your own bias out of your head as well when you can, just appreciate it from a visual standpoint in that sense. So having somebody else, in this case, a child, not somebody creating a new government, but interacting with, different perspectives and ways of viewing the world and different experiences really helped me. I would hope it helped me anyway, stay fresh about my data and not get too into the weeds and kind of read into things. And everyone always laughed and then I got the neighbor kids involved as well. It's like, okay, microscopy time. I need you guys to describe these to me. What do you see? How would you,
It helps you get out of your head.
Yeah. And it was fun. And then they're also learning some visual literacy and some science as well. But, I try to hang out with non-scientists as much as I can because even if I do hang out with scientists, people in different fields, but non-scientists sometimes I'm sick of tired of talking about science all day, and I learn a lot, and it challenges me to explain things in a different way as well when I'm interacting with other people. So, yeah, all the scientists listening, go out and make some other friends.
Right.
Get out of the lab, do something.
Get out of your echo chamber a little bit.
Yeah. It's good to have fresh eyes on things. I mean, a lot of times when you look at data, you're looking for something specific. You're sort of looking to find what you were looking
exactly.
for.
Yeah, it's hard to not do that,
Yeah.
We're not trying to, but especially if you are really excited about your hypothesis and you want it to work, you kind of can to read into things, and I think that's part of the scientific process. The interpretation of data can be fluid, depending, field to field, especially in biology. It could be a little bit more fluid, I feel like. So that's just the reality of it. But if you want to be a good scientist, I think it's really helpful to do that and have input from other people that are not trained in the way that you are trained, right? Because the scientists were really trained to think pretty methodically,
sure.
Which is good, but
being a little spontaneous doesn't hurt.
Yeah, do something weird.
Yeah, for sure.
So, yeah, I think that's good advice for everybody. Go interact with other people. Yeah, and maybe keep an eye out for Bahram's book on chemistry and entropy.
Yes, I would definitely love to read a book that you write.
Well, thank you. Yeah. Maybe someday.
Fingers crossed. All right. Thank you so much for joining us today.
Oh, thank you for having me.
This has been delightful. Thank you. I have a million other questions that I would love, specifically poetry. I'd love to talk to you about poetry some more, but maybe we'll have you back on sometime since you're here at Notre Dame with us. So
sure.
All right. Well, thank you so much again.
Thank you.
Yeah. And thanks, Shahir.
Thank you. At the end of our show, we would like to thank you, our lovely listeners, and our awesome audience for spending your time with us. We thank the Notre Dame College of Science and the Indiana University South Bend College of Arts and Sciences. Special thanks to the wonderful people at the Notre Dame studios. Coming to you from beautiful South Bend, Indiana, in the heart of the Rust Belt, this is Rust Belt Science. I'm Shahir Rizk.
And I'm Maggie Fink.
And we'll catch you next time.